Hello, and welcome to my lab report. I'm Robert Pig, and I'll be your guide. For this lab, instead of modeling an object from a video, we were given precise motion data of a much more interesting subject, a black hole with a star in orbit. Using this data, as well as GlowScript, we were tasked to find the black hole's mass by calculating FNet and solving for the mass of the black hole. I found the black hole's mass to be in the range between 1.59 times 10 to the 34th kilogram and 1.68 times 10 to the 34th kilogram. Later, we will discuss why I identified a range of values. In this lab, each person was given a unique set of data, and so my data showed a star on an ovular orbit where the black hole is not in the center of the path of the star. This lab is particularly important as it shows how fundamental physics principles can be applied to analyze any system, be it ordinary objects analyzed in prior labs, or even something as massive and unimaginable as a black hole. These applications also allow us to approximate real-world data, such as the mass of the black hole in this case. The structure of the rest of this report is going to be as so. Next, I will talk about the data given and the system it describes. Then I will talk about the physics behind the program that analyzes the data. From there, I will answer some interesting questions brought up by the lab, and then finally, some final thoughts and conclusions. Let's look at the data. The movement and placement of the star and the black hole are predetermined. As you can see, the star orbits around the black hole in a non-circular orbit, and as it gets closer to the black hole, it speeds up, which makes sense because the force of gravity is stronger at closer distances, so as the star approaches, it should speed up. This speed up gives it the speed it needs to travel further away from the black hole, giving the orbit shown. Along with the motion data, we also know the mass of the star, which is important in the next step of analyzing the data. Using the motion data, we can extract the mass of the black hole. To do this, we must repeatedly apply Newton's second law. Newton's second law states that Fnet times change in time equals change in momentum, or equivalently, that Fnet equals change in momentum over change in time. Using this, as well as the formula for gravitational force, we can find Fnet and then solve for the mass of the black hole. In the first step of the code, we find v initial and v final using a list of the velocities given to us. These are not the initial and final velocities of the whole orbit, but instead are the initial and final velocities of each time step, which we set to be 1 day. From there, we can find initial and final momentum by multiplying v final and v initial by the sun's mass, which has the value of 2 times 10 to the 30th kilograms. By subtracting final and initial values, we can find change in velocity and change in position. Then, by dividing change in momentum by change in time, we can find dp divided by dt. In this case, the delta t is 1 day, or 86,400 seconds. This time frame is small enough to give us precise approximation of dp dt. By finding dp dt, we have now found the net force because Fnet equals change in momentum over change in time. Then we can find the components of this net force by using the definitions of parallel and perpendicular force. However, this step is not necessary to find the mass of the black hole. By rewriting the force of gravity formula to find the mass of the black hole, we can plug in known values and find the mass. Because our value of dp dt is an approximation, the found mass will fluctuate during the experiment. As stated before, the mass of the black hole, as approximated, fluctuates during the experiment. It specifically fluctuates between 1.59 times 10 to the 34th and 1.68 times 10 to the 34th kilograms, with the average being 1.63 times 10 to the 34th kilograms. However, this fluctuation, when compared to the total value of the mass of the black hole, is negligible. The fluctuation stems from the limited nature of the dataset, because while precise, it only has values per day, so precision of the mass is limited by this. This lab brings up some interesting questions. The first one is, what is the difference between Fnet and the rate of change of momentum in terms of their parallel and perpendicular components? There is no difference. Fnet equals dp divided by dt according to Newton's second law, so the components will be the same too. The second one is, if the black hole was replaced by another and the motion stayed the same, could we find the mass of the new black hole? The answer is yes. because the mass will be the same as the original if the motion of the star is unchanged. If the mass is different, the force of gravity will be different, leading to a new orbit or even no orbit at all. But since the motion stays the same, the mass has to stay the same as well. And now for some final thoughts. I found this lab particularly interesting as analyzing a black hole seems like a task for adept scientists, but now I feel secure in my ability to use fundamental physics principles to analyze systems of all kinds. Similarly, this lab demonstrates the ability of programs to take motion data and other initial conditions to discover interesting new data. Thanks for watching.